so the next part of the course addresses, you can see that as an extension of the graph-based SLAM approach on pose graphs, so that it becomes a technique which is suitable for online processing, for online operation. Online operation here means that we have a robot that moves through the environment, and at every point in time it obtains a new observation and then moves through the environment. And then we are interested in saying, in building up the graph online. That means adding this observation to my graph by, for example, saying the current pose is related to a pose we have been previously with this relative transformation. In order to do that, we need to have a good estimate or a reasonable estimate about what the graph, the configuration of the graph, because if the configuration of the graph is completely messed up, the only way I can actually check for those correspondences is revisit all nodes and see, for example, if both observations match. The problem if I do that is if I get one new observation in, I would need to compare to every pose where I've been in the past with every measurement I obtained so far. And that's something which is an operation that's very costly. And so I would have to do that in every step n times. So every step would have a linear complexity in the length of such trajectory. And the approach I'm presenting here today is one way to actually overcome that, or trying to eliminate the need of always computing the perfect map at all points in time, and provides an alternative strategy on how to build a map that is accurate enough that we can actually do our data associations, but still are able to execute that online, so while operation we always have a consistent map of the environment. Okay, so just a very, very brief reminder. So we had that graph consisting of nodes. So every of those triangles here is a node of the robot, and these nodes are connected, for example, by odometry information or by observations. And whenever the robot revisits a node, like this one over here, it can actually make the data association saying this pose here is relative to this pose located here, and to this one as well. In order to do that, in order to find those constraints, it actually needs to make this data association I was talking about. So it needs to say, what I saw at that node, I can actually bring in relation with what I've seen here and what I've seen here in order to align those scans and compute the relative transformation. Okay. And so the key idea was, in graph-based SLAM, to use the graph to represent my problem, where every node is a pose of the robot, and every edge corresponds to spatial constraints, which connects those two nodes. And this was what we introduced as this kind of virtual measurement, because we really haven't directly measured the relative transformation between two poses, but we have observed the same part of the environment, and from the knowledge about the environment, I could compute the relative transformation between those poses, so kind of forward step and a backward step, from one observation to the environment and from the environment back to the sensing location. And since this node only contains poses of the robot, it's also called a pose graph, because it only contains the nodes. Every node is a pose where the robot has been. And then what we typically do is we have to do two things. First, we have to build the graph, and then one is to find the node configuration that minimizes the error that is introduced by the individual constraints. I also told you last time that we typically do that with a kind of front end and the back end. So the optimization typically happens in what we call the back end scheme, with an A, of course. And so the front end does data association, so it relates the current observation with the graph we have built so far, and the back end performs the optimization. That means it computes for every point in time, or tries to compute for every point in time, the best possible node configuration, the best possible graph. So, and the optimizer or the back end kind of feeds back the node positions to the front end, typically together with the uncertainties, so that the front end can say, at this node here, the probability distribution of about one of the nodes here is very close in terms of mononobis distance to the current location of the robot. So it's worth investigating if I can actually close a loop here and relate the current observation to the observation which is stored in that node. And so what we know, if you don't want to compare the current data which comes into all nodes we have seen so far, we need to have, let's say, a reasonable estimate about our graph for making these data associations. If we don't want to search the whole graph, only those which are kind of close to my current location. And the problem is, if I need to do that at every point in time, optimize the full map, that is pretty costly. And it may be too costly to do that at every point in time. And what I'm going to present here is one way to overcome that. And the idea is here to not use a single post graph, but to use a hierarchy of post graphs. So we use the post graph we know we have so far, and what we call the lowest level, and then build sparser representations, that post graph, on the higher levels. So on the higher level, we have a node which corresponds to one of the nodes of the lower level, but there are much less nodes in the higher level. So kind of one node in this higher level corresponds to the whole, or represents a whole group of nodes on the lower level. And I can actually build that up as a hierarchical graph. So just to illustrate how that could look like, here we have this kind of, this is one of the data sets we quite frequently use for benchmarking, a sphere data set. So we have a robot that moves on the surface of a virtual sphere. And so this would be the post graph you would obtain with the standard approach. So all the nodes are connected to all its neighbors, and you have this kind of sphere-shaped post graph. If we say, okay, we want to construct a first layer so that every node in this first layer corresponds to exactly one node at the bottom level. So that's direct correspondency. So every node which is in here also exists in this one. But it now on this level does not only represent exactly one node, it kind of is representative for a small node for the neighborhood of that node on the lowest level. So the idea is if I move one node in this higher level, I move the whole group with the rigid body transformation on the lower level. I can take it a step further, I can take the second level of the hierarchy, which is again sparser than this one. So every node in here represents a group of nodes in here, and therefore an even bigger group in this graph down here. And of course, build that out until I may have a single node left. Okay, so why is that useful? It is useful because if we do an optimization only on the higher level, so we forget about these two bottom levels at the moment. We only consider the second layer over here. If you perform an optimization in this graph, this can be done efficiently. Why can this be done efficiently compared to the original post graph?
Fewer number of the constraints.
So a much fewer number of constraints and nodes. So there's just a small subset of the variables which are used in here compared to this one over here. So if I do my optimization here on this node, let's say parameterize this post graph in a smart way, so that whenever I move one of those nodes, let's say I move this node a little bit to the right hand side, all the nodes here which correspond to this one move as well. So what I do is kind of do a rigid body transformation of chunks of groups of nodes in the lower level. This will, of course, be not the perfect solution, because you just move one node and the other one moves a whole subset of the nodes. But the idea is that you, or the hope, let's say that way, is that by moving these whole blocks, you only introduce kind of small errors on the lower levels. So you can see that in a way that optimizing here on these higher levels kind of correct the topology of the scene. So kind of the very, very rough structure. You don't care about the details, just about the very rough structure. And in most cases, actually, this is sufficient to correct the core structure, the rough structure of the scene. In order to say, let's say the robot is currently over here, I only need to look to those nodes which are in the neighborhood, and then I may expand them up to the bottom level and say, these are nodes where I really should check for loop closures, but I can ignore all the rest over here. It's kind of the key idea of this approach. So the idea is to only do corrections on the higher levels, to kind of correct the raw structure of the topology of the scene, and only in areas where I really want to, for example, do my data association, I go down to the lowest level and then search in this lowest level for constraints, for data associations. So the key trick of that hierarchy is to have kind of to pre-filter the majority of nodes which are currently not interested in, because the robot is only interested in its current pose, it's kind of a local surrounding in order to do a data association. So it doesn't care, not necessarily care about the rest, at least not in all detail. It often wants to know rough structure, so if you get, for example, send a command to the robot which is currently sitting over here, go to the other side of the sphere, it's enough if I say, I know how to go there, and while I'm traveling there, I kind of get more and more certain, because then I'm kind of taking out this part in the bottom level to look for data associations. But it's often sufficient to know the rough structure of the environment. So it's one of the key insights that there's no need to optimize the whole graph at every point in time. So whenever I add a new node to the new constraint to a node to the graph. So it's only important for me to know the rough structure of the scene and maybe the local surrounding accurately. The rest I don't care about at the moment. And this is kind of the key insight why this hierarchical approach is actually beneficiary for solving the strand problem in an effective manner. Okay, so to motivate, as I said before, the SLAM front end tries to find loop closures. It's the main task of that front end. And this, if I don't have any information about the structure of the graph, it requires me to compare my current pose or my current observation with all the observations I recorded at all previous poses. It becomes clearly untractable as the pose graph grows and grows over time. However, we can actually, if we know about the configuration of the nodes and their uncertainty, that can dramatically limit the search. So for example, you have the robot. The robot started over here, then moved around through the environment, and then it maybe wants to compute what are nodes which are in my surrounding that I need to check for loop closures on. So it says, this is current uncertainty of the robot, for example. So these are the nodes which are in the uncertainty ellipse of the robot. Let's say the 3 sigma bound. That means the robot is with 99% probability here in that area. So I may check these 3 red nodes for loop closures, but I don't need to check. I need to compare them with the others. So the key idea of this hierarchical approach is actually to quickly find those nodes which are relevant for me and build an accurate map here in my local surrounding. Is there any question about that so far, or what kind of general concept, what we want to do, what we want to approach?
We always use the higher level for the SLAM.
I will come to the details in a second. So it simply depends on, in the end, it simply depends on how many corrections we do. So if I do a big correction on the top level, and I see that nodes which are one level below becomes quite inconsistent, then I may optimize there as well. I can propagate the information downwards until I have a certain level of accuracy. Any further questions so far? So the key insight is the motivation here is we don't need the perfect map to make our data associations. So not the perfect global map. So we are interested in only correcting the rough scene and maybe the local surrounding in a more accurate way. And therefore we build up this hierarchical pose graph. You can actually see this hierarchical pose graph as an approximation of the original problem. First, if we do our corrections only on the higher levels, we kind of do this rigid body transformations of these whole groups. That is still probably close to the correct solution, but it's definitely an approximation because they can't move independently anymore. So if I move them on the top level, I do a really rigid body transformation of the whole group, so I transform all nodes in the same way, and they can't move independently when optimizing on the higher level. Therefore, there's an approximation of my original problem. And this can actually be motivated by 2 facts in the context of a SLAM problem. The first one is typically moves smoothly through the environment, is not teleported somewhere else from one point in time to the next point in time. It means I have these kind of neighborhood relations, these groups that they're kind of related with each other. The second thing is this only becomes quite useful if we have sensors with a limited range. Because if we would have sensors which can see an infinite sensing range, At every point in time, we could see all nodes, and we would get a graph which is completely densely connected. So if I do a small correction over here, I may change the map somewhere else completely. And this is something, if I have that, this hierarchy doesn't really work because everything is connected with each other. But this is not the case in reality. In reality, our observations are local. That means I only have constraints between, or connections between constraints on a local scale. Okay, so let's look a little bit more into the details. How does this thing pull up? So just a small animation or illustration here that works. So consider this is our post graph as the input to our system. So the dense graph which contains all the nodes in the environment that we mapped so far. So now assume we want to build the hierarchical post graph out of that. So the first thing we do, that what I said before, is we need to form local groups. So we group nodes. We do that typically based on their connectivity. So maybe these could be our groups. All these nodes which are close to each other, or which the robot traveled subsequently while moving through the environment, I may form in these local groups. What I then do is I need to build the higher level post graph from this post graph, where one node on the higher level should actually represent one of those groups. That means I need to find or determine or select a so-called representative node for every of those groups. So in the end, every group you can see that votes for one representative, and this representative should represent the group on the higher level. Okay, we can do that. We can just randomly select one, for example. Doesn't really, so the strategy has a big impact on the result. These are the red ones now. So these red ones are now selected at the representative nodes that should represent the whole groups on the upper level. So then this node, for example, says, I see myself relative to the red node in the third transformation. Therefore, if this node moves, the other one moves as well. So if on the higher level this representative is moved in this direction, these nodes will move accordingly. Okay. So on the higher level, this is what my post graph on the higher level looks like. So all the green nodes here are not available anymore. So this graph is much sparser than the original one, so it contains much less nodes and edges. But still, one thing which is unclear is actually how do I actually obtain those edges? The nodes were clear, these were representative nodes. But these edges between those nodes now need to represent all the information I have from these multiple constraints which connect several nodes here in the vicinity of this one and this one, for example. So that's one thing I need to do. I need to compute these edges on the higher level. So these edges here should represent the connectivity between two nodes. So if the two groups, so the group that is represented by this node, the group which is represented by this node, are connected with each other, I want to have also a connection in here, and this connection should, as good as possible, approximate all the connections we have on the lower level among the groups. Okay, is that kind of clear so far? So then I can repeat that process recursively. So I now can, for example, group these two guys, group these three, these two, whatever, and go to the next level. So I can recursively build up my hierarchy until I say, oh, I have kind of a sufficiently small number of nodes on my highest level. Okay, now we build up our hierarchy. We haven't said anything about how is the optimization done. So consider this is our highest level, and we now want to do the optimization. We've said we have those edges, and these edges represent or approximate all the structure on the lower levels. So if I optimize these nodes over here with these edges over here, I also get an approximate solution for the configuration of the post graph on the lower level. So I simply can perform this optimization. So let's say do an optimization from here to here, and I say this is the result of the optimization on the higher level. So now I have update on this higher level. The higher level is corrected now, and this means that on the lowest level I did kind of rigid body transformations of the individual groups. Okay, so let's say it this way. Typically, the robot wants to know its local surrounding quite accurately. Let's suppose the robot is here, somewhere in that local area of that node. So then it may propagate this information downwards here in the center. It goes one level below. It does the rigid body transformation of the nodes down there. So I had these originally two nodes. So this sort of position, these were the kind of neighboring nodes. I had my pulse graph on the lowest level. So it kind of does the transformation of these nodes down here. And maybe if this, so I can use these nodes now on the lowest level to render my local map accurately, optimize it on the lowest level to make them more accurate, just in a very local scale. And then I can actually build a local map from this one over here and then check what is the uncertainty of the other nodes to check for the closures. This was kind of the idea high level, and what I want to do is now dive at least in one or two aspects of that in a little more detail. So the first thing we do, when and how should we actually generate a new group of nodes? As I said before, it turns out that the way you group those nodes is not that relevant to the overall results. It can have an impact, but it doesn't necessarily has to be. And the easiest way is you simply say, whenever the robot travels more than 10 meters, or n meters, I just create a new group and accumulate all of them head so far in a local group. And whenever I create a new group, the first node is my representative node. It's a very, very easy strategy. It can be very easily implemented, and I have one way for obtaining those groups. The way you select the groups can have an impact, as I said, on the overall structure, on how to optimize, can simplify your problem or make your problem a little bit more difficult to solve. You may have a little bit more edges on the higher levels if you select the groups in a suboptimal way, so kind of the connectivity of those nodes you may consider. The problem is that kind of finding those optimal configurations is typically already an NP-complete problem in these graphs, whenever you have whatever, cutting the graph in a way that you have minimal number of connections between groups. It's all a very, very hard problem, so we say just ignore that here, because it turns out that the impact on the result is not too big. The second question we have to argue is, when should we propagate information downwards? So if we did our optimization on one level, when should we actually propagate information downwards and do the corrections really on the real physical node, on the nodes which directly correspond to the road pose at a certain point in time? And you can argue that you can do that if you introduced a big change to those nodes. So if you did a really, really big change, a local structural change, it makes sense to render that information if I need it. Quite often you may argue, I don't care about most parts of the graph, not at all, if I want to make data associations. I'm only interested in subparts of the graph. So it should be a combination of, have there been dramatic changes, and do I need that information at all at the moment to make data associations? But this is not the case. There's no point, no need to do these optimizations, unless you have either too much computational resources you want to waste at the moment, and you can actually do that, or do these optimizations because you say, I may need to use this information in the future. Right now I have computational resources available, so right now I do my computations. These are all valid strategies, but most of the time, following the lazy strategy is actually a pretty good idea. Just don't do it if you don't need it. And then the two key informations is how to construct actually this graph and how to construct the sparse edges. It was something I just haven't explained yet. So if you move from one level to the next level, how do you get those constraints on the higher level so that they, as good as possible, represent the nodes on the lower level, and how to propagate the information downwards when optimizing. Okay, so we can now actually exploit the information from last week and from the kind of add-on to chapter 15 I presented before, on computing the this constraint Z over here for those two nodes. So this is the lower level, and have all those connections over here. The first thing what I have to check is, does there exist a connection between those two groups? If so, I need to put an edge in here. what I can do is I just fix all the nodes in the, so I can just take out those two groups and build a new graph, which is exactly those edges, and I just optimize this small subset, just these two groups. I do the optimizations of these two groups, independently of the rest. And this, if I then look to these two nodes, say, given these two local structures, ignoring the rest, they should be, every certain distance, they should be apart if the optimization of this small subset converged. So I do the computation over here, and after the computation has completed, I just compute the transformation to come from this node to this node, and this will be kind of the virtual observation for my new edge on the higher level. Just a virtual observation which result from a local optimization of this subtype. And in a similar way, I can obtain also the information matrix by having computed the result. I kind of fix one of those nodes, I cut them out from this H matrix representing this local structure, and then I'm only interested in the block of the inverse that corresponds to these nodes. This gives me the relative uncertainty of this node with respect to this one. I just invert this small, tiny information covariance matrix again, and then have my information matrix that corresponds to this edge. If I perform in this way, I obtain a new edge which corresponds to the result of the optimization of those two groups together with the relative uncertainty that results from this joint optimization. You had a question? Okay, not anymore. Perfect. Okay, any further question or any question about that at the moment? So what I do is, just as an illustration what I said before, I optimize those two groups together, ignoring the whole rest of the graph. So just kind of make a small copy of this small part and just optimize this small part independently of the rest. And then I simply obtain the relative transformation between XA and XB on this higher level by just computing the transformation in between those two nodes in the resulting optimization. And then I need to compute the corresponding information matrix. And this I do by taking the H matrix corresponding to this subset, I invert it, so I compute the covariance matrix. Then I cut out the block that corresponds to this variable B, so the B block of this matrix, and invert that. So I've written in here the information matrix between A and B on this higher level of my post graph corresponds to the inverse, cutting out the block BB and inverting it again. Then I have, of course, I go from information form to covariance form. Then I can simply cut that out to compute this uncertainty relative to the other one, and then inverting it back. So that's something that I can typically actually do because these subgraphs are typically small. These are small groups, so this optimization is fast, and I can obtain this constraint on the higher level. Okay, so now you know how to compute the edges, the observations, the length of the edge, the transformation of the edge, and the corresponding information matrix on this higher level. So the next question is, how should we actually propagate this information downwards? So we said we have our nodes on the lowest level, and the representative nodes here on the higher level correspond to actually, they are actually physically exactly the same node. So if I move this one in the optimization, so if I move them in or out, I just make a rigid body transformation to those groups over here. So just move the corresponding node. So if they move, for example, further together in this example, based on the optimization I perform the higher level, I kind of just shift those two groups closer to each other. And then I can simply do a strategy. If this update was large to this lower level, then I can start optimizing the post graph of the lower level as well. First, then I say I kind of move these two blocks into each other. Maybe it's worth to propagate the changes downward and optimize it. If the change is not too big, I may completely ignore that and say, I'm fine with the rough structure of the environment. So these are all the ingredients I need. I need to know how to build up this hierarchical graph, and I need to know how to propagate the information downwards. So building up the graph upwards is what we did, was finding these new virtual observations and information matrices and how to, in a kind of heuristic way, propagate this information downwards here. Okay, so the nice thing is every of those steps doesn't take too much computational resources, and it allows me to compute the rough structure of the environment quite efficiently. So I can actually use this for online processing. So whenever I get a new observation in, I can perform this structure over here. If I want to use it to just compute, given all constraints, compute the best map, I would just do, what I would need to do is I just would kind of build up the hierarchy up to the highest node and then propagate the information once downwards, always propagating the information downwards until I optimize the lowest level. You may ask yourself, why is this actually a good idea to do that? Couldn't I just take the input and optimize it with the standard approach we used so far, just only the lowest level? It's actually true that this, if you're lucky, it gives you the same result. The thing is that this hierarchical approach is typically better if you have big errors in terms of the initial guess, because by combining those nodes and moving those nodes with the rich body transformation, you typically get a better initialization of the overall problem if you once walked up the hierarchy and then layer by layer optimize it downwards. You can see that as getting better and better initial guess until you do the optimization on the lowest level. So if you don't have local minima, it wouldn't make a difference, but in reality you have local minima, and therefore this approach can be helpful, especially in terms of not those smooth error functions, or if you expect a lot of local minima. Here's just a very few examples how you can actually use this approach. So this is one data set that, so there's a picture of a parking garage at Stanford, and it's actually work of Diana who did that a few years ago using the autonomous car. The Stanford team to actually build a map of this environment, and then the map can look like this. So you can see here traversable and non-traversable areas, and then you can actually do autonomous parking tasks. So you leave the car in front of the garage, they park the car. The car uses this map to locate itself and drive in there and park the car. And so this part of the work in here only looks on how to build a map, how to steer and drive the car. That was worked on by Rainer. And so the question is, we want to now use this hierarchical approach to build a map out of that, and just have a small animation. What you see here on top is kind of the lowest level, all the nodes which come in during the optimization, and here in blue you see the higher level, so the second level of the optimization. What you can see, you see a lot of small dots which are created over here while the car drives, and here you see the core structure. And what you can also see is whenever the robot revisits an area, it will always create new nodes here on the lower level, but on the higher level you typically don't add new nodes. So you only have multiples over here because you have different floor, different level in the parking garage. But on the higher level, you don't need to add nodes all the time, because you typically can say, this is still a node which belongs to a local group, so I have already a node on the higher level. You may update the edge information, but you don't have to. And so as you can nicely see here, the thing in the blue graph over here gives you the rough structure of the environment. You can roughly see the topology of the scene, where this one is expected to provide much more detailed information. But if you're just interested in what the environment roughly looks like, it's typically completely fine to use this structure to, for example, search for possible data associations. So you can dramatically speed up your search for data associations if you operate on this blue graph here compared to the red one all the time. Another small example, so that's the Intel Research Lab data set, so the picture I've shown before already. So you can see here again, these are two levels. You see the red ones created all the time, and the blue ones just from time to time. Here you can nicely see the effect. So there are new nodes added, and the red one, there for every node where the robot is, you add a red node, but whenever you're close to the blue one, there are no new nodes created on the higher levels of the hierarchy. It's just the case that we may update the edge information because they still belong to this local group, so you can assign this node again as belonging to this one local group. And then if you optimize only the blue graph, you involve much less nodes, much fewer nodes, much fewer constraints. Therefore, the optimization is substantially faster and is completely sufficient to estimate the rough structure of the environment. And you can use this then to check in which areas you should look for loop closures, where you then may go down to the red level but only in these areas where you really need it, and not in the rest of the environment. You can actually show that this hierarchical post graph is definitely an approximation to the higher levels compared to the lower levels, but the approximation error to is not too bad. So when you see these are a few data sets where Intel and Stanford are these kind of real world data sets, and the others are artificial data sets, typically with much bigger errors. And you have actually two values in here. The one is the probability mass that is not covered by the approximation, computed in a way that you say, for every node of the representative nodes, we compute the 3 sigma bounds, that I can draw the ellipse, and compare that to the ellipse we would obtain on the lowest level. We don't do the approximation, and simply see how they relate to each other. And once you're interested in the probability mass that is not covered on the higher level, and this is kind of the dangerous thing, that you're too certain on the highest level that you may not look for data associations you could find on the lower level, so you may become overly confident. And there's the second part, the probability mass not covered. The probability mass which is outside, so this is kind of the area which is too big, if your uncertainty ellipse is a little bit too big. That just means you may look for too many data associations. This may cost some extra overhead, but typically doesn't screw up your problem. So it's also kind of a small illustration. So this is this Intel Research Lab, just for the representative nodes on the second level. It's actually the lowest level, the first and the second one, although the first one you don't see good in green. And you can see there's different ellipses here representing the uncertainty of the individual nodes on the different levels. So the red one is the one on the lowest level, so the real result you're interested in. The blue one is your approximation. There's a small area which is not covered, so that's a dangerous area. And here is the probability mass, which is where the ellipse is kind of too big. But basically means you're more uncertain, and you may need to, your system may check for more nodes as possible candidates for data association. But quite likely the system will then determine that this is not the case, because you don't find a good match in there. But at least you don't miss too many. So it's kind of a reasonable approximation, these higher levels of the post graph. And the advantage is that they are much, much faster to compute. So kind of to sum that up, this hierarchical post graph is one way for creating an approximation of your problem, if you only work on the higher levels, which corrects to the core structure of the environment. So you get kind of the topology out, if you want to see it that way. And the big advantage in here is that this is very fast to compute, and you can use this to actually dramatically speed up your search for data associations. And that's why it's interesting, especially for online mapping applications. So when you get rid of online mapping, you may be interested in these approaches. Even if you just offline mapping, just do the optimization, it can be helpful or beneficial if you have bad initial guesses and local minima. Is there any questions so far about that? Okay, so this is the original work which proposed that. There's also some other content in there, but just the hierarchical optimization is the relevant part here. There's also an open source implementation if you want to play around with that, which you find here under this address, where you can download the optimizer and actually play around with that, visualize the different levels of the hierarchy. So in case you're interested in that, this information is available, that system is available. Okay, any questions? Okay. It doesn't seem to be the case, so thank you very much. Make a short 5 minutes break, and then we continue with the landmark-based slide.